Good morning, everyone. Welcome to lecture number 5 in this sequence of 13 modules, weeks, lectures in introductory statistics, 12 of which include new material. The last one is a summary, perspective kind of thing. So after today, we're 5/12 through our stuff. That's a good fraction. After next week, when we hit the break, we are halfway through in terms of numbers. That's a good number. Good time to have a break. Today, some of my repetition is part of today's lecture, since here's the plan for today's lecture. We're gonna jump into the mean once again. Like the first day I met you, I asked you to compute the mean of some school grades, and I also told you how to compute the mean, and I also shared with you my sort of impression that this is something we have done for years and years, ever since we was in the second or third class in elementary school. We have heard about the mean or the average of numbers. So that is maybe almost embarrassing that now in lecture 5 we are going to once again talk about the mean on a major Danish university in lecture 5. We still talk about second grade stuff here in lecture 5. Actually, I'm quite embarrassed when I see the books of my children. I look at the books and say, hey, I can make exam questions in this stuff in my course. And so, that's the Danish public elementary school, no private stuff or anything. Danish, so pretty good there. Anyway, you're pretty good also, or you will be, of course. We are not embarrassing, of course. We're just taking it a bit further now. We are taking it further on how we're going to think about how we can use the mean. And we have done enough of probability babbling around. Now we're going to do really statistics, right? Statistics is what we call, with a finer word, we call it inference concerning means. So that's the new thing we're going to do with the means, not just compute them, we're going to use them for statistical inference, right? That's how we're going to use them. For doing that, we have some general stuff that we need to think about, and then we come to the actual tool. The actual tool that is known, and you saw it in my scientific paper from the cellular fauna and cancer thing, the actual method, the actual tool of today is coming at the end, of course, so don't leave us. It's coming here, it's a confidence interval. And we are having some steps toward moving to this confidence interval method. So, here we begin with these steps. Almost begin, because let us introduce the example. The specific example I will play around with during today's lecture before we dig into the very general abstract things to sort of be able to cope with this. Let's read together what this example says. So this is, we think we have a car manufacturer here who would like to determine the petrol usage of highway driving for a new make of a car. So you make a new engine, you make a new car, you want to test it, right? That is illustrating the everyday life of any production company out there. From previous times, pilot study, basic sort of historical knowledge, we believe that we know something. This is an assumption we're going to loosen up by the end of this lecture, but for now, we make this assumption coming here. We make the assumption for now that we know the noise in the system, we know the variability in this system that we are going to plan and observe now. We believe that we know that from car drive to car drive, from tests, sort of measurement to measurement, there is a certain variability in the petrol usage, and this variability is 0.2 liter, measured as a standard deviation, 0.2 squared, measured as a variance, liter per 100 kilometers. So that is sort of a knowledge that we assume known and true without any questioning at this point. Then, what we are facing here is, the way we're going to do it is that we have the same driver go and make 25 times driving 100 kilometers. Wouldn't that be a nice job at Lamborghini or Ferrari or something like that? Go drive 25 times 100 kilometers in this Ferrari. Thank you. Let me do that. Almost as exciting as being a statistician, of course. Anyway, what we in this company, if you're the manager of performing this test, probably you as an engineer, you're not going to sit in the car and do this driving. You're going to have someone do it for you. You will be the manager of this whole thing. The question that we already touched on last time that we should be asking ourselves to be intelligent about this mean coming out of this, we're going to compute the mean of the 25 measurements, of course. What we should ask ourselves is, in fact, this question. To be intelligent about the value of the mean, what can we use it for? How much of worth is it to us? That is what in math language is called, what is the variance of this average, of this random average? Sometimes it has one value, sometimes it has another value. What is really the noise in the average? Is it the truth or is it highly noisy? The mathematical version of this question is, what is the variance? And then we're going to be able to calculate something that it takes in this probability thinking in something that we call a maximal error. That's coming down the line in not so many minutes. So that's what we're going to do. We're going to read the first part of chapter 7. Ideally, you should have read it already, according to my suggestions of how you do your work in this course. I would suggest that's a good idea. The tools are in the beginning of chapter 7. Some of the basics for coming to the tools and why the tools are working is coming from chapter 6, and we'll refer to chapter 6 for that. For instance, a very, very important new distribution today called the t-distribution that we're going to be using for these tools. And of course, we're going to dig into R throughout, as we do all the time. So here's the deal again. We've been here before, but let's do it again. The way we are thinking of this is that we have a population. We use the word population. It could also be more sort of, it's the truth, it's the real world out there, it's the ultimate insight and complete knowledge of this random system that we are facing. This is what we could call the population. Now, in this case, the population is given by, in fact, mu, the true, I'm talking about the petrol, the true sort of average petrol use for this car, under certain conditions, of course. And then this variability in the system from sort of car drive to car drive. There is a natural variability. Even though you set up some conditions, there will be natural variability in this system. Now, what we are going to do is that we are going to have, you could say, a smaller subset of this whole. Wouldn't it be nice to have complete information? But that's an infinite thing, and it's infinitely expensive to achieve infinite information. So it's not the optimal thing to go for. We don't want complete information because it's too expensive, and we will never be finished in our lives. So we'll have to deal with finite information. The finite information is the sample, in Danish, stikprøve. The actual data that we are facing. The whole inference thing that we are going to deal with in the rest of this course, basically, is this arrow. That's the inference, statistical inference. That is what we are doing. That is using numbers to infer, to say something about the world, the truth, the situation we are in, the future world maybe, the unknown part of the world. We want to infer about something which is larger, that goes beyond the actual numbers that we are having. We want to use it to go beyond the numbers in a way. That's the inference. Now, for the inference to make good sense, as I'm stating, the sampling mechanism, and this is this one, this is, you could say, the way that the data are actually produced or collected, right, is important for whether or not the inference arrow makes good sense. It's like we need to have representative measurements for what we're interested in. It's, in a way, it's just putting common sense into some framework here. Of course, if we sample, if we go away from the business with car manufacturing and go to sampling the population of Denmark, knowing about who we are going to vote for the next election, or which we'll of course get back to in this course, polls in the US for the presidential election, that comes in very handy in this course. We'll get back to that. When you do that kind of sampling, that's what we call sampling, that you take out, you ask people, you measure either the petrol use or you ask people, who do you vote for? One thing is a continuous measurement, the other thing is kind of a binary, a discrete thing, right? In this process, it cannot, it's not enough to say go to Wall Street in New York, for instance. Go on Wall Street and you make a sample on Wall Street. You ask all the people passing on Wall Street. 90% of Wall Street people in the morning, they come in suits and work in the financial area. So, if you ask those, you don't obviously get a representative sample for the whole population of the US, which is a difficult thing to achieve. It's easy enough to say that you don't have it, it's more difficult to actually obtain it. So, it's just to say, this representativeness leads to certain awkward or sort of tedious attempts like this, to try to define the situation such that we do not have this problem. There is a definition of what should be okay in order for us not to have a problem. Well, one way of ensuring that we are okay in the inference, that is to make sure that we have a completely random sample. A completely random sample, to make sure that it's random. Now, how could we define that to be more specific? Well, here we make a distinction. We make a distinction between a finite population, just to let you see the next slide, where we will have a similar definition for infinite populations. So we distinguish between finite populations and infinite populations. Finite populations, that could be, for instance, the Danish population. You might want to consider that as finite. I'm sure that US people would consider the Danish population, even if they know the existence of the Danish population, they would consider it very, very finite. So, if you sample something which is finite, sample meaning you start measuring, you should be sure that the numbers, the observations that you achieve, you could say the set of observations you achieve, all possible sets of n persons here should have exactly the same probability of being chosen, right? So we take a handful of you at random. That's kind of a hypergeometric setting here, that we take a handful of you completely random. Now, we express in a way the same thing, slightly more abstract, in what I call infinite populations. In fact, basically everything we do in this course will be dealing with so-called infinite populations. And infinite populations, that's because these are also, you could call them abstract populations. You could call them kind of future populations. Like when you measure the car, the engine of the car. What is the population here? Is it finite? Well, it's a bit odd. Is there only a finite? No, there could be infinitely many drives with this engine now and in all future, right? You cannot point out this, there is only this amount of drives in this car in all future. It doesn't make sense. You don't have a clear definition of any finite population here. That's another way of saying it. Also, if you test, like if you're Novo Nordisk or others, if you test medical treatments, cancer treatments, typically the population that we are facing is, it's not those 100 people having this illness. It's those people now and in the future in the whole world that will have and get this illness. This is the population that we are dealing with. It's an infinite and abstract population. So this concept can be rather sort of challenging in the comprehension of it, but in practice it doesn't really ruin the world for us. Just the populations are out there, they are in our course, most of it, infinite. We say that a sample from such a more abstract / infinite population is a completely random sample if they all follow the same distribution. I mean, like there is maybe a height distribution or an age distribution or a petrol usage distribution with a mean and a variance. They all come from the same distribution and they should be independent from each other. So it's not like we can collect, I mean, if we collect persons, we shouldn't sample people from the same family. If you call people and ask them who you vote for, you shouldn't ask, then let me have your children, let me have your wife, let me have anything. Then you get, you have a big family, so you get 5 votes for the same person from this family. That's not independent information. You have to call 5 different persons in 5 different families. So that is related to the independence. Now, that was a bit of abstraction here. Let's focus on the means now. The abstraction, I jump back to my picture here. The abstraction is that we have a population given by some mean and some variance, and that we do proper sampling. So basically, most of what we discussed in this course, we assume that the sampling has been done in a proper way. Complete random sampling is such a proper way. Now you know that the definition is there. In everyday life, this can be a crucial part. And when you see discussions in the media about results for different types of experiments and studies, often it's not so much whether you use this or that statistical tool. It's more the basic sampling. Was that really done in a sensible way, such that the numbers really represent what we would like to know about the world? That can be a difficult discussion. And yeah, anyway, it's just to say we're not digging into the sort of the detail or the substance of this discussion in this course. Now we get to the tools, assuming that the sampling was okay, right? So we already saw that we should use the estimator. I mean, we should compute the average when we have a number of x's. What I emphasize here now is that this is also random. That's why I use a capital X here. This is the key issue to understanding how we become intelligent here. To consider the average. In a given experiment, we will have one average only given to us, the outcome of the experiment. However, the way we're going to be intelligent about it is to realize, to understand that this is only one possible outcome. We could just as easily have had other outcomes, right? Next time we do the same experiment, we get another outcome, being a new average. And if we do the experiment 3, 4, 5, 6, 7, 10, 20 times, we make this meta thinking. What if we did the experiment many times? What if we had many different samples of the same size? What is then, how will the average from sample to sample behave? That's the key question, right? If it behaves with a very low variability, it's the same thing every time, whoa, then it's a very good average, right? The single average we have would then be a very good average if the theory would tell us that if we repeated things, it would still maintain the same thing. It has a low variability. That's a good average. If the theory tells us that if I repeat this, it would it would jump in all directions, then it's not a very good average in this case, right? Here is the result. The result, and this is something that we saw, actually, that this comes directly from there's a little, actually, a stupid error here in this place. It should say, not capital S, but sigma squared. We assume sigma is known, so forget about the S here. It doesn't make sense. It's the variance as we know it, as it's given. Because you have seen the variance rules that we played around with last time with the airline passengers. That's where we used the rule that if we take the variance of an average, let me use the summation sign, then we first use the rule where we take out the 1 over n, that becomes 1 over n squared in the variance rule. Then we use the variance of the sum. The variance of the sum is the sum of the variances. And since we have n of those variances, we assume that a variance of a single one of those, that's the situation, that a variance of one of those is sigma squared. Then there are n of those, so we have n times this variance, all of it divided by n squared, and altogether we are left with the formula that I just told you. The magic formula telling that variability of averages decreases with n. This is the reason why I'm here, why we can work with statistics. Because noise decreases with the size of the experiment, right? As n increases, the variability decreases. I think common sense would have told us that back already, maybe not in 2nd grade, but then in 7th grade or 8th grade. I said we would have known that common sense would have told us this, but here's the formula for it, right? That sort of supports this common sense and makes it explicit, and also tells us whether it's not easy to know whether it's n or n squared or whatever. It's n on variance, it's square root n on standard deviation. So, more specific on the sampling distribution of the mean when sigma is known. Yeah, what do I mean, the sampling distribution? I've tried to convey that that's the key question. How does the mean change from sample to sample? Not that we do many samples, we only do one sample, but the way we should think is in terms in this meta way. What if we had many samples? How would the mean, the average, how would the mean change from time to time? What is the distribution of the mean? Well, first of all, we are told something here from chapter 6, that the mean itself, I've told you that already, is in itself something random from sample to sample. And here is the result then. The mean of the mean, in fact that makes sense if you write like this, the mean of the mean becomes the mean. We're in lack of words here. But anyway, the mean on average hits what it should hit, actually. That's a good property that we probably never thought that it could be any different. In fact, it can. Like if we compute not the mean, but the median, as we saw. The median is not exactly like that in all cases. It can be like that, but not in all cases. And then the result that I just told you, that the variability of a mean is sigma squared divided by n. I mean, this is just repeating basically what I showed you on the slide from before. So there is a distribution, we call it now a sampling distribution. I'll skip this one actually, because we're not really going to use it in the course. We have a similar expression for a finite population, which is basically the same. We just have kind of a hypergeometric variance factor here that changes the picture a little bit. Let's not spend time on that. Let's see, have this one as the final slide of this little recording of the very abstract recording, very abstract part of the beginning here. Just showing you a bit of, giving you a feeling of that there's a bigger world out there in terms of theoretical and statistical framework for what we are doing here. Even though I said in the beginning we are very naive, we are just talking about the mean of some numbers today, and how would such a mean behave from a statistical perspective. This is just illustrating your first step into the rest of your life and the rest of the world. That is, computing a simple mean of numbers is just one little version of computing something based on numbers. I hope you have this feeling. I mean, out there we can compute many different things, and your future life will consist of. I'm sorry, you can't help it. If you take, as I said, an academic education, and you go for business, or you go for research, or whatever you go for, you will base a lot of the things you do in the future on empirical information, on numbers coming out of different studies and investigations. Whenever we look at numbers, something comes out of the numbers. And this is what we in statistics generally call that we estimate something. And here very abstractly we call it theta hat. Theta is a sort of acronym for anything we could imagine computing out there. Not necessarily only the mean, anything we could compute. And whenever we are doing statistics, we are thinking of this actual computation. The hat illustrates that this is something we have computed, theta hat, is actually a guess, an estimate of something underlying, some underlying truth, that we are using theta hat to be a guess of theta, to be an estimator of theta. So that is like we use the average to be a guess of mu, right? It could be very general. Then we can think of properties of such ways of computing things. And that is what statistics is doing for you, even though you're not going to be statisticians maybe. But you'll have to face the fact that you'll have to work together with people who are actually working with this, or the numbers are there in your company and you have to be sort of maybe a 10% statistician or 20% statistician. There are many of those out there among engineers and others that you have to work with numbers, even though you're not an expert necessarily. You have to think about the properties of what you compute. What we compute can be good or bad in two ways. It can on average hit the right thing. It's like if you throw an arrow, or if you throw an arrow, what's that, a bow or peel? If you what's that? Bow and arrow. If you imagine this skew. Target, thank you. The words are disappearing on me. Then you could be very precise. You could on average hit the 7 with 3 or 4 arrows in a row, right? But hit it at the same place. In that case, you would be what here is known as, you would be efficient, you would have a low variability, but you would be off the target. So you would have what is known as a bias, or you would be non-central. So these are the two properties that estimates can have. They can on average hit the right thing, and they can be more or less variable in their properties, right? So if an estimator is hitting the right thing, we call it central or unbiased. We like that. That's a good and sound feature, property of estimates, that they are having this property. Not all estimates that we use necessarily have this property, but it's a nice property if they have it. The mean has this property, no problem. Then we could have different estimators of the same thing, and then we say that one estimator is more efficient than another estimator if it has a lower precision. The better precision, the more efficient, right? It's just, I mean, we're not going to follow this road here, this tangent of theoretical considerations further than this slide. I'm just having you, for now, think about, in this course, we compute things. We have to think about whether we, on average, hit the right thing with what we compute, and the precision of what we compute is important, right? Compute. These are the two properties that we should be worried about. We will be very much focusing on the precision, assuming for many of the things that we compute that they, on average, are okay, which they are for many of the things. Okay, we make a jump to the next recording here.